So, hello everyone. We'll start in let's say 2-3 minutes, so a few others can join the session too. So, we'll start in 2-3 minutes. Okay, so I guess I'll start. There's a few of you already in the meeting. So, hel- so hello everyone. I'm Lakshay Saggi, the discrete maths problem solving sessions TA for the Tuesday sessions. So this will be our first session. So hello to everyone. So uh, today in today's session we'll be mostly covering the week one problems related to the week one of the discrete maths course, which were based on Boolean logic and stuff. So I have some problems prepared, which I'll just share with you guys and I'll start discussing them also. So if you guys have any doubts in the solutions, whatever I'll be discussing, you guys can ask your doubts in the chat, and you guys can ask in the chat anytime you wish. So I'll try to answer to the best of my ability. So also, if my voice is not clear or there are some issues with my screen sharing or audio, then you can let me know in chat and I'll try to fix it, guys. So yeah, that's all for this. So I'll just share my screen and we'll get started with the problem statements now. So I hope I am clearly audible to you guys. So just sharing my screen. Wait a second, guys. Okay, so I hope my screen is visible to everyone. So there's a Google Docs which has like session one and some questions written on it. So can someone let me know via thumbs up or in chat if if my screen is visible? Okay, it's visible. Thanks, Shruti. So I'll get started with discussing the problem statement. So the sessions will be like this only. So I have some problem statements prepared and I'll try to discuss these problem statements with you guys and you can ask doubts if you have in the solutions of these. And if you have any other doubts over the week, you can also ask me in the chat box and I'll try to answer those also in the session. So firstly, let's start with these problems. So the first question is so in the first question, basically we are given uh, these three Boolean expressions. So the first question asking which of the following is are satisfiable. So we are given these three Boolean expressions and then none of the above option, and we have to answer if uh, any of these expressions is satisfiable. So what are satisfiable expressions? So let me just uh, remind you guys the definition of satisfiable Boolean expressions. So the Boolean expressions which are true for at least one assignment of Boolean variables. So uh, I think this must have been discussed in the lectures also, but I'm just trying to remind you guys about everything. So yeah. So what are satisfiable Boolean expressions? So the expressions which have a truth value of true for at least one assignment of Boolean variables. Note that for some assignment, the Boolean expression might be false, but what we need is there must be at least one assignment in which it is true. Even if in all other assignments it is false, then also we'll say it is satisfiable if there exists at least one. If a Boolean expression is true for all the assignments of Boolean variables, then it's called a tautology. And similarly, if it is false for every Boolean assignment, then it's a contradiction. So this satisfiable Boolean expressions are something in between tautologies and uh, let's say contradictions. So contradictions are always false, tautologies are always true. Satisfiable Boolean expressions are sometimes false and sometimes true. So uh, okay, Shashikant, I'll increase the font size. Uh, Is this better now? Shashikant, is it better for you now? The visibility? Okay, a little more. Uh, does this work? Okay, nice. So this works. So yeah. So yeah, so I was discussing the definition of satisfiable Boolean expressions. So yeah, so Boolean expressions which are true for at least one assignment of Boolean variables. So now what we have to do is we have to answer which of the following expressions are satisfiable. So for each of these expressions, we just need to check whether there exists at least one assignment of Boolean variables in which this expression will have a truth value of true. So do you guys want to try this out yourselves? So let's say the option A is for option A. Is it satisfiable or is it not satisfiable? Option A is P implies R if and only if, not P or Q. Would you guys like to try it out and answer in chat, or maybe should I discuss it myself? Okay, so maybe I'll try to answer, and if you guys come up with some solution, you can type in chat along the way. So I'll just write this option again. So I'll be using a bit different notation. So yeah, let me just familiarize with you guys with a bit of notation which I'll be using. Like the questions have this sort of notation, I'll be using the notation of this sorts. So notation. So for any expression, let's say Boolean variables P or Q, I'll write it as a P plus Q because, or it can be thought of as a Boolean addition or something like that. So, like I like to write it instead of P or Q as, or the P conjunction symbol Q. Instead of it, I like to write it as P plus Q, just because I feel it's a more cleaner representation. So this is just a notation. So you guys can adopt any notation you like. This is a notation which I personally like because it reduces a lot of the clutter. So yeah. Similarly, the expression for expression P and Q, I'll be using the notation PQ. So this is because like the AND operator can be thought of as like a multiplication. So note that this is not this plus and this PQ are not actual multiplications. These are just notations for OR and AND. So P plus Q, like if P and Q both are true, or let's say, so then this true plus true will give true only, because true or true is actually true only. So yeah. So this is some notation which I'll be adopting. Similarly, not P, I'll be writing it as this exclamation P. So I hope this notation is clear. This is a notation which I'll be using in a lot in like all the solutions because I personally feel that this notation is much more clear. Although it's up to you guys when you are solving these statements on your own, what notation you want to adopt. This is my personal choice. So yeah. So let's just come here. So option A here is so option A. So we have to check whether these expressions are satisfiable or not. So the first option is P implies R if and only if not P or Q. So let's just write this option down. So in the notation which I prefer. So yeah. So this is the expression like P implies R, and this is the double implication arrow, not P plus Q. And we have to tell whether this is whether it is satisfiable or it is not satisfiable. So you guys must have seen in the lectures, I think, that uh, an expression of P implies Q can be is equivalent to actually maybe I'll write it as a precursor. Uh, Let me just rearrange the ordering. So you guys must have seen in the lectures that something like let's say P implies Q is actually logically equivalent to not P plus Q. So this is because like if this statement P implies Q is true, if P is true and Q is true, and it is also true whenever P is false. So that's why this is equivalent to not P plus Q. So this you must have seen in the lectures. I'm assuming you guys already know this. So let's just see now. Like P implies Q is written as not P plus Q. So this P implies R if and only if not P plus Q can be written as not P plus R. Uh, because like I'll just resolve this I just written this P implies R as not P plus R, and then the if and only if uh not P plus Q. So, so. So this is something which I arrive at, and this if and only if expression, you guys must know that uh, A if P if and only if Q is actually equivalent to let's say P implies Q. So this is sort of a bit of a revision also for you guys. So just bear with me. So P if and only if P double implication arrow Q means P implies Q and Q implies P. So P implies Q and Q implies P will be nothing but like P implies Q multiplied by Q implies P because I'm using multiplication for the AND operator. So resolving these P implies Q as not P plus Q, writing this P implies Q as not P plus Q, and similarly writing Q implies P as not Q plus P. So this is something which we get, and uh, this further resolves to. Maybe I should use some arrow here, right? Uh, so this is not actual equal to sign because it is not exactly a mathematical equality. It's more of a logical equality, as in this expression is logically equivalent to this expression. So that's why I did not want to put an equal to sign. Instead, I put something like a equal to colon sign to signify that it's a logical inequality and not an actual mathematical equality. So yeah. So after this, you can resolve this basically using distributive properties, and this will using distributive properties of the expression, distributive properties, and for like the AND operation. So this will basically resolve to not P times not Q plus P. So actually, like this is similar to multiplication only that this will resolve something like this. Like we'll multiply this not P into not Q plus P, and then this Q into not Q plus P, and add those two expressions. So let's just see what happens. Like I'm just experimenting and seeing like what sort of things will happen if we simplify this. So this is not that much related to problem, but more related to the understanding of the logical expressions. Not Q plus P. And similarly, now this plus symbol will come, and now I'll multiply this Q with not Q plus P. Q times not Q plus P. And now this will logically be equivalent to, now I can again use the distributive properties here. So not P will be multiplied by not Q and added with not P times P. So P times not P will always be equal to 0 because not 0 exactly, but false. Because P and not P is false. You guys must know this already, right? So this expression will actually simplify to uh, P times Q. You guys can check this yourselves also later. Plus not P times not Q. So this P double implication Q is essentially this expression. It can be replaced by this expression of PQ plus not P times not Q. So I hope the steps which I have done make sense to you guys. If you have any doubt, you can ask me also. Otherwise, I'll just resume. So the interpretation for this double implication operator is you can use a truth table of P and Q also, but the main interpretation is this expression is true. This P if and only if Q is true. If either both P and Q are true or both P and Q are false. Only for true and false values will this expression be true. You guys can check this here also. If P and Q both are true, then this PQ term will evaluate to true. And so true plus anything will be true. Similarly, if P and Q both are false, then this not P and not Q term will evaluate to true. And so this whole expression will be true. But if one of those is true, but if P is true and Q is false, then this expression like will be false and this expression will also be false. So false plus false will give me false only. So that's why this P if and only if Q is only true when either both P and Q are true or both P and Q are false. So this was the main idea which I wanted to give to you guys. You can keep this sort of thing in mind also. Uh, that P if and only if Q is equivalent to this term. But I don't think we'll need that here itself. So I have actually resolved this P implies that if and only if not P plus Q to this. Not P plus R if and only if not P plus Q. So now I want to just check whether it has a satisfying assignment or not, right? So if it has a satisfying assignment, then the value should be true. Like satisfying assignment means that for specific assignment of variables, the term should evaluate to true. And for the expression to evaluate to true, this if and only if expression to evaluate to true, either both of these values should be true or either both of these values should be false. So we can just see like if we set P to false, like let's just set P to false. So if P is false, then this not P will be true. So this whole term will become true. Similarly, this not P is true. And so this whole term becomes true. So true and this double implication true will give me true only. So that's why it is satisfiable. Easy to see that it's satisfiable. And when is it satisfiable? Like at least for this case, like whenever P is false, okay, I'm just changing the symbols a bit. Nothing, nothing fancy. I just want the notation to be consistent across the document. That's why. So yeah. So yeah. So what we have actually shown here is that option A is satisfiable. Maybe I'll just highlight that since it's the answer. Yes. And it is satisfiable as we can see like whenever P is false. Like at least whenever P is false, what happens is this not P becomes true. So this side of the expression becomes true. This not P becomes true. So this side of the expression becomes true. And true if and only if true, like true double implication true will be true. As we have seen that P and double implication arrow Q is true when either both are true or both are false. So another assignment could have been when both of these expressions are false. In that case, also that sort of assignment may also result in this whole statement being true. But yeah, at least for this case, we have seen that it's satisfiable whenever P is false, irrespective of the values of R and Q. So I hope this is clear to you guys. Uh, so I can move on to next option. So this sort of problem may seem a bit trivial to you guys, but I'm trying to discuss all of this from the start because, like, personally, I feel that in discrete maths or let's say in Boolean logic, the basics are much more important to cover because if you know the basics, like you can solve any problem. So the problem which may seem complex at first can be rather easy solved if you are clear with the basics. So that's why I'm spending more time on this sort of trivial problem and these sort of trivial stuff, so that everyone can have a good grasp on all these basics. So yeah. So the option B here is now P implies Q or P implies R if and only if Q implies R. So let me just write it down in my notation. Uh, P implies Q plus P implies R, and this whole is in parentheses if and only if Q implies R. So yeah, so this is the option. So basically P implies Q and P implies R when the OR of these two expression is taken, if and only if Q implies R. So we have to see whether it has a satisfying assignment or not. So let me just reduce this P implies Q to not P plus Q and see where this goes. So I don't know the answer to this problem. I'm just uh, doing it along the way by reducing the problem. So not P implies Q will be not P plus Q. And now this is added with P implies R. P implies R can be written as not P plus R, not P plus R. And now it has an if and only if implication. I'll just leave that as it is. And this side is not Q plus R. Right. So uh, we also know, I hope you guys already know so this is nothing but not P or Q and whole of this odd with not P or R. Like plus corresponds to R only, as I mentioned in the notation. So what this means is actually the OR operation is an associative OR operator is an associative operator. So what this means is that the order of evaluation is not important. Like not P plus Q is in parentheses, but we don't need actually this parentheses. So these parentheses can be removed and the ordering of this P, R, and Qs can be changed among each other. I hope you guys already know this since it must have been covered in the lectures. So this can be just reduced to like removing these parentheses. So this will be nothing but I'm just reducing this left side of the expression. I'll keep the right side as it is. Let me just see what happens then. So I'll just reduce that not P plus Q plus not P plus R. And this is in uh, if maybe I'll just put all of this in next line. Yeah. So this is in if and only if relation with not Q plus R. So now this uh, not P plus not, so I can change the ordering among these since OR operator is also commutative. So this not P plus not P can be taken together and it will just resolve to not P only because A or A, like an expression P or P is just P itself. So this can be resolved to nothing but not P plus Q plus R. I hope I'm making sense to everyone. And this is an if and only if with not Q plus R. So this is sort of the final expression which we arrive at. And like we can also open up this if and only if, but I would rather like to see it as a black box and just see whether there exists an assignment where this holds true and this also holds true. So if we arrive at such an assignment, then we are done. So I hope this makes sense to you guys. So like what I'm saying is just that option B resolves to this sort of expression. And now for this to have a truth value of true, uh, let's just view this expression as E1 and this expression as E2. So E1 double implication with E2 will be true either if E1 and E2 both are true or either if both are false. And we can easily see that E1 and E2 both can hold true at the same time easily by assigning R a truth value of true. So this can be seen like easily, it's sort of an oral exercise. So if I set R to true, irrespective of values of P and Q, like this expression will be true. And similarly, this expression will also be true if R is true. So true if and only if with in relation with true will give me a value of true itself. So that's why option B will be satisfiable at least whenever R is true. So I hope I'm making sense. So yeah. Yeah. Uh, Again, I'll just write, copy this only that it's easy to see that it's satisfiable and it is satisfiable whenever R is true. So I hope the solution made sense to you guys. So now let's just come to option C then. So option C was the expression this P implies Q and P and not Q. So I'll just write it down again in myself. So this is P implies Q and not P and P and not Q. So and I'll replace it by multiplication. Like, it's not actually replacing my multiplication, but just by the notation. So this will be P times not Q. So because P and not Q will be just nothing but P times not Q. So this is the sort of expression which is given in the problem statement. So again, the first step which I'll do is, as you guys have already seen in the previous solutions, that I'll just resolve this P implies Q to not P plus Q. And I'll write it down as not P plus Q. And this will be multiplied by P times not Q. And again, like a similar reasoning to last time. Last time, what we did was we had these pluses together and the parentheses, and we said that the OR operator is associative. So actually, we can remove this parentheses, and as it's commutative, we can also move around these terms. Similarly, here we the AND operator actually is also associative and also like it's commutative, so we can remove this. So you can see that here is an and, like here is a multiplication, like between not p plus q and this expression p and not q, and here's a multiplication between p and not q. So actually the order of multiplication does not matter. Like this p and not q can be evaluated first, or this not p plus q times p can be evaluated first and then ANDed with not q. So this can just be written as let's say not p plus q times p and times not q, not q. And it's up to me to do the multiplications. Like earlier, this parenthesis was forcing me to do these multiplications first and then with this. But actually, since it's an associative operator, I can do this multiplication first also. So I'm referring to AND operation as a multiplication and OR operation as a addition, but actually, keep in mind that it's actually logical OR and logical AND. So now what I'm going to do is I'll just multiply these two first. And then what I get is P times not P. So similar to the distributive property. So this P will be multiplied by not P, and P times not P, like P and not P will always be false. So I can ignore that. And plus the expression will be P times Q. So this expression will just resolve to P times Q. I hope I'm making sense, guys. If you feel if you get confused, you can ask in chat anytime. So what I'm saying is this not p plus q times p will resolve to p times q only. So this will resolve to p times q, and then I'm multiplying it with not q. So now again, since the multiplication can be performed in uh, any precedence, so now I multiply this q with not q, and I obtain basically false. Q and not q is false. And then when this false is again multiplied with p, irrespective of value of p, I'll always get false, right? Let me just write it down a bit more. So this will be p times q times not q. And since this q times not q will always be false, So irrespective of value of p, like even if p is true or p is false, anything ANDed with false is always false. I hope you guys remember this. So that's why since this expression evaluates to false, any value of p times false will always result to false. So it is actually equivalent to false. So option C, this expression is actually always false, irrespective of the assignment of Boolean variables. So that's why this option C, this expression is actually not satisfiable, because for all assignments, for no assignment, basically, this expression evaluates to true. It evaluates to false for all the assignments. So that's why this expression is not satisfiable. It is not satisfiable as it is false for all possible Boolean assignments. So yeah. So basically, you can say that option C is actually a contradiction, because contradiction is something which is always false. So yeah, I hope I make sense. So if in the first question, actually what we have obtained is option A is satisfiable, option B is satisfiable, and C is not satisfiable. So the question was asking actually which of the following expressions are satisfiable. So we have shown that first and second are satisfiable, third is not. So the correct answer is basically option A and option B. So correct answer, I'll just highlight this also. Option A, comma, or maybe I'll just write it as uh, A, comma, B. Okay, so we have solved this first question. So if you have any doubts, you can ask in chat. So now we come to second question. There's some doubt in chat. No. Okay. So let's just come to the second question then. So second question is a bit oral question only, and I hope that you guys can answer this yourselves. So let's just say a number x, x is some number which corresponds to number of satisfiable assignments in a tautology that involves three variables. So x is the number of satisfiable assignments in a tautology that involves three variables, and y is the number of satisfiable assignments in a contradiction that involves nine variables. Then what is the value of y by x? So tautology and contradiction is something which I've already discussed with you guys, and you must already know. So uh, I believe you guys can answer this question yourself. So what will be the values of x and y? So any guesses in the chat? So x is the number of satisfiable assignments. So the number of possible Boolean assignments which resolve to true in a tautology that involves three variables. Okay, so maybe I'll try to answer. So for guessing the since tautology, so the idea behind this is that let's say we are calculating x. So x is the number of satisfiable assignments in a tautology that involves three variables. So a tautology is something which is always true, right? This has been covered in lectures. Since a tautology is always true, so any assignment of Boolean variables. The key idea is any assignment of Boolean variables will be satisfiable. Does this make sense? An assignment, a Boolean assignment is said to be satisfiable if the expression resolves to true. And since a tautology expression is always true, so any assignment of Boolean variable will always be satisfiable. I hope what I'm saying makes sense to you guys. So what this means is that we can take any assignment of Boolean variables, and it will be satisfiable. And since we have three variables, so how many assignments are possible? So since there we have three variables, each of these variables can take a value of true or false only, right? There are two possible values for three variables. So the number of assignments will be 2 raised to the power 3. So since there are three variables, number of possible assignments is equals to 2 raised to the power 3, which is 8. So here I'm calculating x. I mentioned this, calculating x. So since tautology is always true, any assignment of Boolean variables will be satisfiable. Since there are three variables, the number of possible assignments is 8. So what we get is the value of x is 8. Now let's calculate the value of y. Now we'll come to calculating y. So what is y? Y is the number of satisfiable assignments in a contradiction that involves 9 variables. So does anyone want to try this in chat? Like, want to try to answer this in chat? This is a straightforward calculation. So a contradiction is a statement which is an expression which is always false, irrespective of the Boolean assignment. So maybe I'll cover this one. So since a contradiction is always false, what this means is that no assignment of Boolean variables will be satisfiable, because an assignment is satisfiable if the expression resolves to true in that assignment. But a contradiction is always false, so no assignment will resolve to true, and so no assignment will be satisfiable. So since y was the number of satisfiable assignments, so y will be equal to 0. So y will be actually equal to 0 only. So since we wanted to calculate the value of y by x, so the value of y by x will actually be maybe I'll just write here only. Hence y by x is actually 0. Okay, maybe I want to keep this in this way only. So yeah. So I hope this makes sense, guys, because this was not too difficult of a question. And this was the main idea behind this was that a tautology is always true. So every assignment will be satisfiable, and a contradiction is always false. So no assignment will be satisfiable. So yeah. So let's come to the third question then. Uh, so third question is saying, uh, choose C and F equivalent of the following compound statement. So we are given this statement, not P if and only if not Q implies, let's say not uh, implies A implies B and Q. And we want to find a CNF conjunctive normal formula. So you guys must have seen in lectures basically what is a conjunctive normal form. So conjunctive normal form is nothing but a CNF. The definition of CM, I'll just be revising, is basically an expression which can be broken down into expressions of the form, let's say E1 multiply and E2. Basically, it can be broken down into multiple expressions uh, separated by an and. So this is the main idea behind conjunctive normal form. And it also has the property that where all EIs are just contain only or operator. So I hope this definition makes sense. So CNF form is just conjunctive normal form. So basically what it says is that it's a form of an expression where the expression is broken down into some n expressions, and the final expression can be written as E1 and E2 and E3 and E4 till and En. And all of these E1, E2, E3, E4 only contain the OR operator. So let's just say E1 can be P or Q or R, but it can't be P and Q. It can only contain the OR operator. So a CNF form will be something like P, like in my notation of plus and multiplication, it will be something like P plus Q times Q plus R times R plus P and so on. So basically, the idea of this form is to separate out the ands from the ors. So the upper level expressions are the higher level expressions are separated by ands, and these expressions in themselves are separated by ors. This is an idea behind conjunctive normal form. Similarly, there is another form which is called disjunctive normal form. So I'll just write DNF also. So you guys must have seen these in lectures, but I'm just reminding you guys. So in DNF, the roles of ands and ors reverse. So basically, in DNF, we separate the we separate the expressions via ors, and these expressions in themselves within themselves are separated by ands. And like note that these two are not like different, like some expression will have an CNF form, some expression will have a DNF form. So every Boolean expression can be converted to either a CNF form or a DNF form. Like these are also interchangeable. A CNF form can be converted to a DNF form. Similarly, DNF can be converted to CNF. Like these sorts of things you must have seen in the lectures, like how to construct a CNF or a DNF form from a truth table for an expression. So yeah. So these are the two forms, and the basic idea behind these is to like simplify some calculations and something. So yeah, but let's just get into the question then. So the question is asking, so we are given this expression. Let me just write down this expression. It is not P if and only if not Q, and implication implies uh, A implies B, and this is ANDed with Q, so multiplied with Q. So this is the expression E. And now I want to see which of these expressions, this Q or P and this, like these are three expressions, which of these expressions is actually equivalent to the compound statement. So let's just verify whether these three expressions are actually of the CNF form, conjunctive normal form. So, so maybe contain only all operators or operators and literals. And operator and literals. So literals are basically something like P as well as not P. All of these thoughts like Q can also come, not P can also come, not P can also come, like inside these E1, E2s and E3s. So that's why I was calling these literals. So yeah, it's just a small different thing which I added. So yeah, maybe I'm just trying to save space, although it does not matter, but I like so that everything is in one line. So yeah. So let's just see first whether all of these uh, so we have to check whether which of these is basically equivalent to the expression E. And we also need to actually see that whether these are in their CNF form or not. So let's just see. So CNF form is basically where the higher level expressions should be separated by ands, and the expressions themselves within themselves should be separated by ors only. So here we see like this Q or P is an expression E1, and this not A or B or not P or Q, not Q is another expression, and both are separated by ands. And these expressions are separated by ors. So this is in a CNF form. Similarly, it's easy to verify that the second option is also in CNF form, and third option is also in CNF form. So at least we know that all of these options are in CNF forms. So now what we want to see which of the following is actually logically equivalent to this expression, this formula of not P if and only if not Q implies A implies B times Q. So we have just seen that these are these expre like from like all of these are in CNF forms, but maybe like some of these might not be actually logically equivalent to the expression E. So we just need to check which of the following is actually equivalent to expression E. So again, following the same procedure, or let's say the recipe for resolving the Boolean formulas, I'll just be writing out some stuff. So yeah. So I'll just be opening this double implication arrow here also, just because I think it will be necessary. So this, like I already said that P times Q, P if P and double implication arrow Q is nothing but P times not P plus Q times not Q. So similarly, not P double implication with not Q will be nothing but like I'll just be opening up this term first. So this will be nothing but not P times not Q and plus not of P, which will be P itself, times not of Q, which will be Q itself. So note that like not P double implication with not Q is actually logically equivalent to this expression, which is actually P logically equivalent to P double implication Q. So actually not P double implication not Q is essentially same as P double implication Q. So this expression, opening this expression to this, does this make sense to everyone? Is everyone fine with this? Because I'll be doing a lot more stuff here. So you guys need to pay attention. So this not P times not Q can be opened up written as this, just because P double implication Q is just PQ plus not P times not Q. And now inside this, uh, what I'm going to so this expression implies, so implies I've just copied as it is, this A implies B times Q. So opening up this A implies B. So this A implies B can be written as not A plus B times Q. So note that one thing I just want to point out, one thing which I want to point out earlier, but I just forgot. So note equivalence of two expressions can always easily be checked using by comparing the truth tables. So note that if we are given some two expressions, even any two, and you want to see whether the both the expressions are equivalent to each other. So it can always be checked by checking the truth tables and seeing whether for all the variable assignments, the values are always equal. The expression values are always equal. So this is a very trivial way to check equivalence of two expressions. But note that if the expression has n variables, then the truth table will be of size 2 to the n. So truth tables can be very large in size. So since truth tables can be exponential in size, this method can take a lot of time. So this truth table is a very heavy hammer actually, by which we can solve all the equivalence expression problems. But the main issue which arises is suppose there are 10 variables and there can be to the power 10 possible assignments. So you'll need to check over 1,000 entries of the truth table, whether those entries are equivalent for two expressions. So that's why even though truth table is a universal way of doing so, we try to avoid it because it can have very high computation cost and stuff. So that's why like I'm trying to resolve this expression E into some simpler form so that I can directly see whether it has what's its CNF equivalent. Like I could have easily done that using truth tables also, but I want to avoid truth tables as much as possible. Because here also like there are five variables P, Q, A, B. Okay, there are only four variables P, Q, A, B. So truth table will be of size 2 to the power 4, which will be 16 entries. And I want to avoid 16 entries also. So yeah. So just doing this stuff, here I get this. And yeah, so I'll just be writing it a bit more cleanly. This is just PQ plus not P times not Q. And this is an implication with not A plus B times A plus B times Q can also be simplified to like not A times Q plus using distributive properties as not A times Q plus B times Q. So this will be nothing but not A times Q plus B times Q. Yeah, just move this around. So I hope I'm making sense here. And from this, what can be done is I'll now try to remove this implication sign. And this will result in like, let's say E1 implies E2 will is nothing but like not of E1 plus E2. So this will be nothing but like not of the first expression, which will be not of PQ plus not P times not Q. So I hope I'm making sense. So this expression, like this E1 implies E2 will be nothing but not of E1 plus E2. So not of E1 is nothing but this value, not of this E1 plus the E2. E2 is this value. I'll just copy it and add it here. And since addition is associative, I can remove these parentheses. So this is the expression I arrive at. And now this not of PQ can be resolved to this. So you must have also seen the De Morgan's law, I believe, right? That this not of PQ actually, maybe I'll just add this also as a note. Uh, that not of PQ is actually equivalent to uh, not P or plus not Q. So this is De Morgan's law. Basically, what it says is that negation of P and Q is actually equivalent to negation of P or negation of Q. So you can check this using the truth table also, like if PQ both are true, then this is false. And here also it will be false and so on. So I hope this has been seen in lectures. And similarly, this not of P plus Q, basically here there was a not between P times Q. Here it's an not of P plus Q. This can be actually written as not P times not Q. So De Morgan's law is basically to take negation of an expression, just invert the individual Boolean variables by their negations and replace all the ands by ors and all the ors by ands. So this and here between P and Q was replaced by an or between not P and not Q. Similarly, the or between P and Q was replaced by an and between not P and not Q. So I hope I'm clear to everyone. Like because you guys are not interacting much in chat, so I don't know if you guys are properly able to understand. So I'll I'll advise you guys to be a bit more active in the chat so that I can know if everyone has understood or there is some doubts. Because everything is sort of in my mind, right? Whatever I'm saying is something which I already have in my mind. So if whether I'm able to deliver it properly or not will depend on your feedback, right? I'll only come to know about it if from your feedback. So okay, so Hemant is saying at least this part is understandable. So yeah, nice. So now, so these are the two De Morgan's laws. So now what we are going to do is, so now I'm trying to open this expression. Like this was the expression which I had obtained till now. Like I had simplified E to this expression till now, and now this not of whole of this expression, right? So I'll try to use these De Morgan's laws to open up this expression. So this expression can be opened up as, so this not of PQ plus not P time not Q can be just written as not of PQ. So like maybe I can just write it like, as we already said, that replace all the pluses by multiplications and all the multiplications by pluses. So this will be nothing but not P plus not Q. So this PQ will become not P plus not Q. This plus will become multiplication and it will be multiplied with negation of this. So negation of this term, negation of not P times not Q will be uh, actually negation of not P times not Q will be nothing but replace P by not P, which will be just P itself, and not Q by like Q by not Q. So not and not again will cancel and it will result in Q. And their multiplication will become addition. So this expression actually, this of not of PQ plus not P time not Q will become this expression. So I hope everyone is able to understand. So yeah, Asif, so you're saying that you didn't revise. So that's why I'm also trying to uh, remind you guys a bit about everything which was discussed in class, like these De Morgan's laws and what are CNF and DNF forms. So that's why I was trying to revise, uh, get a bit of revision done also along the sessions. So, but yeah, I'll advise you guys to see the lectures before coming to these sessions so that you can understand the problem solving better. So yeah. So this not of PQ plus not P time not Q resolves to this, and I just write this expression as it is. Plus this. So I've resolved E till now up to here. And further resolution I can do, what I can actually do is I can again open up this parentheses to simplify this term. So this not P will be multiplied with P and it will become false, so we don't need it. Similarly, this not P will be multiplied with Q, so this will become not P times Q, and then this not q will be multiplied with p. So this term will also be added. So not p times q plus not q times p, and then plus this expression as it is. So I have to clear that I just resolved this expression to this expression. And so we have a much cleaner form. Uh, so this form is basically actually not a CNF, but rather a DNF form we have obtained. So we have, as you can see, like there are these pluses, and these pluses are actually separated by expressions which are only multipliers of each other. So I hope this makes sense. What I'm saying. Uh, so what I'm saying is just that this is actually a DNF form because these expressions are just individually separated by these. The literals in these expressions are separated by and on a higher level, all of these expressions are separated by ORs, which was the definition of a DNF form actually. So instead of CNF, actually, while driving, I resolved it to a DNF form rather. But no worries. Uh, yeah. So this can be, I believe, uh, be seen as a DNF, as a CNF form also. So, so we wanted actually to see like, so note that one thing I want to point out another was like CNF form for an expression is not unique. Same expression can have multiple CNF forms. So, in fact, one expression can have infinite CNF forms, in fact, because you can always add something like a tautology and tautology and tautology with some CNF form. So, a CNF form will not change even after that. So there can be infinite CNF forms, and we just so there can be a case that like more than one of these forms is actually a CNF form. Like this is also CNF form, this is CNF form, this is CNF form. So everything is possible. Like maybe all of these three options are CNF forms. We don't know. It is possible that all are CNF forms. So for checking this actually, yeah, so we'll have to check all of these expressions individually, whether option A is equivalent to this expression which we have obtained. Like we could have directly checked with whether this option A is equivalent to the initial expression, option B is equivalent to the initial expression, option C is equivalent to initial expression. But initial expression has these implications and double implications, so it becomes a bit complicated. That's why I first like to resolve the initial expression into somewhat simpler expression, and then try to see whether like then I'll just try to see whether this option A is equivalent to this expression, then option B is equivalent to this expression, and option C whether option C is equivalent to this expression. So now should I give it to you guys or maybe not? Or So yeah, I think we will. If I try to just check for for these expressions individually, we'll run out of time because I have to discuss some more problems. So this is the simple expression which we have obtained, and now let's say this is a homework for you guys, or you have to try it yourself. Uh, So this was the expression which we had obtained. This was the simpler expression. And now you should try yourself that which of the expressions in the options is actually equivalent to this simplified expression. So the approach will be to check the equivalence will be like, let's say we are given this option A. So, so yeah, one more thing. So when you see this option, when you see this expression E in this form, like in this DNF CNF forms, so DNF CNF forms are very useful also in the sense that they also give us an idea about the truth tables. Like suppose we are given this option E and we want to see in what at what Boolean values will this option E be true. So this expression E, I've simplified to this expression. So now if I want this expression to be true, then since these are multiple additions, at least one of this addition must be true. At least one of these terms, at least one of these forms must evaluate to true. So we can individually set each of these terms as true. So let's say this not p times q is true. And at that at that Boolean assignment, the whole E will be true. And when this not q times p is true, at that point also E will be true. Similarly, not a times q is true, at that time also E will be true. And similarly, when b times q is true, at that time also E will be true. So individually, we can say that E will be true when BQ is true. So that means when B is true and Q is true. So whenever B and Q both are true, then E will be true. Similarly, whenever Q is true and A is false, at that time also E will be true. Whenever P is true and Q is false, at that time also E will be true. Similarly, whenever Q is true and P is false, at that time also E will be true. So from this, we get an idea of the truth table of E also from this DNF form. So these CNF and DNF forms are useful for this also, getting an idea about the truth table. Similarly, let's say we were given CNF forms. And from these CNF forms, we wanted to see uh, which at what values will the expression be true. So we can get somewhat of an idea by checking, like for the expression to be true, all of these E1, E2 up to En, all of these should hold true. For that, E1 should be true, and E2 should be true, and till En should be true. And using that idea, using similar idea, we can get an idea about the truth tables also. So yeah. So just like this was just an idea which I was just saying. So if you guys want to see if you guys want to check the equivalence between, let's say, this expression and, like, let's say option A, so what we can do is let's just see if the truth assignments actually match. So actually when BQ was true, it means B was true and Q was true. So whenever B was true and Q was true, then E was true. So let's just put B and Q as true in this option A. So in option A, if B and Q are true, then here this not A or B or not P or Q will resolve to true because B is true. Similarly, here Q or P will resolve to true. So this will resolve to true and true, which is true. So at least when B and Q are true, this E is true as well as option A is true. Now let's just check this not A times Q. So if Q is true and A is false, then E is true. So Q is true and A is false. If we put it here, we can get some, if A is false, then this side becomes true and Q is true. So this side becomes true. So something along these lines also you can try to do. Otherwise, a very basic hammer to try is like for option A, what you can do to basically check whether it is equivalent to the simplified expression. Just open up this parenthesis like I did here. Like I open up these parentheses. So here also you can use distributive properties. So this will become something like Q, and so I'm just listing out possible approaches to do this question. So this approach is basically open up all the parentheses. So this Q or P times not A or B or not P or Q can just be written as Q times not A plus Q times B plus q times not p plus q times not q. And similarly, this added with p times not a plus p times b. So this will resolve to a DNF form again. Like this can be converted into, this is a CNF form. It will be converted to a DNF form if we open these parentheses, if it makes sense. What I'm trying to say. So I'm just trying to say that open up this parenthesis and see what terms come. And then term by term, it will be easier to compare whether E and this option A are equivalent. So that's one of the basic ideas. Another idea you can try to check the equivalence between two expressions. So yeah, I hope I'm clear, although I have not solved this question fully, but I think I've given enough ideas to try this yourself. Yeah. So the main idea which I was referring to was just open up this option A also and just check whether these two have truth assignments at the same values. Yeah. Now let's maybe move on to question 4. So yeah. So the question 4 is actually so choose the valid conclusions given the following premises. So uh, so uh, these are some statements given to us. Like if the police were able and willing to prevent crime, they would do so. If the police were unable to prevent crime, they would be impotent. If the police were not willing to prevent crime, they would be malevolent. Police do not prevent crime, and if the police are good, they are neither impotent or malevolent. So from these statements, we want to see which of the following are actually valid conclusions. So which of the conclusions can actually be derived from these statements? Or let's say which of the following conclusions can be inferred. So we'll need to use something like laws of inference here. So I'll try to do this question orally. I don't think it's too difficult to see. So here, like this is a statement: if the police were able and willing to prevent crime, they can do so. If the police are unable, they would be impotent. If the police were not willing, they would be malevolent. Police do not prevent crime, and police are good, they are neither impotent or malevolent. So the statement here given to us, one actual statement which is given to us is police do not prevent crime, and other statements are more like if statements. So let's just see if this statement holds true, then what are the conclusions we can derive? So police do not prevent crime. So if the police do not prevent crime, so okay. Basically what happens is the police do not prevent crime. So if the police do not prevent crime, there can be two reasons for this. Like as we can see from other statements, basically, uh, police is either unable to prevent crime or it is not willing to prevent crime. So there can be two cases, right? Uh, Either police is uh, unable to prevent crime or it is not willing to prevent crime. Like crime cannot be stopped because of two reasons. Either they actually are not willing or they are unable. Or both of these is also applicable. Like they are willing but not able to prevent crime. That time also crime will not be prevented. So it will be something like so either police are unable to prevent crime or they are not willing to prevent crime. At least this we know from the fact that police do not prevent crime. Since police do not prevent crime, either they are not willing to prevent crime or they are unable. So not willing or unable. So if they were unable, then they would be impotent. And if they were not willing, then they would be malevolent. Right? But we don't know whether they are like they are either they are unable or unwilling. So they are either impotent or malevolent. We don't know for sure whether they are unable to prevent or they are not willing to prevent. But if they were unable, then they would have been impotent. And if they were not willing, then they would have been malevolent. And we know either they are unable or not willing. So they are impotent or malevolent. At least this conclusion we can draw. Right? So I hope this is clear to everyone. So the correct conclusion would be police are impotent or malevolent. So answer will be, let's say, option B. So option B is correct because police do not prevent crime. And since they do not prevent crime, they were either unable to prevent or not willing to prevent. So they were impotent or malevolent. Also, the last statement says that if the police are good, they are neither impotent or malevolent. So the contrapositive for this statement is actually uh, if the police are impotent or malevolent, then they are not good. So A, the contrapositive for A or A implies B is like not B implies not A, right? So if the police are good, they are neither impotent nor malevolent. The contrapositive for this will be uh, if the police are impotent or malevolent, then they are not good. Does this make sense to everyone? What I'm trying to say here? Like this same statement can be interpreted as it's since contrapositive is same as the original statement. So this statement can also be interpreted as if the police are impotent or malevolent, then they are not good. So we have already shown that police are impotent or malevolent. So this also implies that they are not good. So option B, comma C is actually the correct answer. So since police were impotent or malevolent, so they are also not good because of this last thing. So yeah. So is this clear to everyone? I'll move on to the next question then. So I had prepared actually 10 questions, but I don't think I'll be able to cover all of them. So I'll cover this fifth question and then I'll directly jump to the last question since it's an interesting problem. So yeah. So coming to this fifth question, the options are written in a bit messy way here, but you guys will be able to understand, I think. So the fifth question is saying, so let's say we are given 10 elements, uh, x size are from 1 to 10, and so we are given basically 10 elements and x size are the propositional variables. So x1 up to x10 are 10 Boolean variables basically or propositional variables, which are true if the ith element is in the set X. So which of the following expresses the statement there are at most 3 elements in X. So basically, there are 10 elements and this x1 to x10 variables are the variables for whether ith variable is in set X or not. So we are choosing a set X from the 10 elements. And now we want to say that there are at most 3 elements in X using these variables. So does the problem statement make sense to everyone? So we are given 10 elements. Out of that, we are choosing some elements in set X. And now using the propositional variables x1 to x10, I want to say the statement that there are at most 3 elements in X. Okay, it makes sense. Nice. So if the problem statement makes sense, then maybe you guys can try to see. These are actually the four options. So the first option is like, let's say, this notation is nothing but I'll just try to tell you guys what this notation means. So this notation is nothing but we are taking and so these are basically these caps are all and conjunctions. So we are taking multiple conjunctions over expressions and like let's say the innermost conjunction is taken first. So this option A means that we take xi1, xi2, xi3, xi4 and we take their conjunction and then its negation and we do it for all I4 from I3 plus 1 to 10. And then this, all of this is done for all I3 from I2 plus 1 to 9. And this is done from all I2 from I1 plus 1 to 8. And this is done for all I1 from 1 to 7. Similarly, in option B, what we are doing is we are again taking like conjunctions in these forms. Similarly in C and similarly in D. So uh, basically, can you guys try to answer? Like, so basically, like these all these ands over I1 from 1 to 7, I2 from 1 to 8, I3 from I2 plus 1 to 9, and I4 from I3 plus 1 to 10. These are sort of basically done to uh basically I'll tell you the intuitive idea. So these ands over all these I1, I2, I3, I4 are done to ensure that we cover all possible cases of selecting four elements out of at least four elements from the set X. If what I'm saying makes a bit of sense. So maybe I'll just give you an idea of option A also, like what the option A is saying. So we want to say the statement that there are at most three elements in X, right? So we can also express the same statement in a way that uh, uh, there are like if there are at most three elements in X, then this same statement can be proven by proving that uh, there are not at least four elements in X, right? If there are not at least four elements in X, then there are at most three elements. I hope this makes sense. So what option A is doing is it's taking and over all possible I1, I2, I3, I4. So it's choosing basically any four elements xi1, xi2, xi3, xi4, and it's saying xi1 is present and xi2 is present and xi3 is present and xi4 is present. So it's saying that four elements I1, I2, I3, and I4 are present. And it has a not in its front. So it's saying this is not possible. So it is not possible that four elements I1, I2, I3, and I4 are present in X for all I1, I2, I3, I4. These these indices are mostly for taking over all the I1, I2, I3, I4. So actually option A is correct. Correct. And why is it correct? Because as it says that uh, there does not exist four elements I1, I2, I3, uh, I1, I2, I3, and I4 such that all four elements are present in X. For and it says this statement for all I1, I2, I3, I4. So basically it says that no, there does not exist four elements, any four elements which exist in X. So this sort of captures the criteria that there are at most three elements in X. Because if there were at least four, so there could be four or five or six, then there must exist some four elements exactly at least, which would be present in X, which option A states is not possible. So option A is actually correct. Now option B. So this question is more about interpreting what Boolean formula is saying. So yeah. So now what the option B is saying is it's taking an AND over all I1, I2, I3, and it says xi1 and xi2 and xi3. So xi1 and xi2 and xi3 means I1 is present and I2 is present and I3 is present. And it's saying that this is true over all i's. So this is actually incorrect. So it's just saying that uh, all possible triplets of elements are present in X, which just basically means that all elements are present in X, which is not what we want to state. So I hope I am making sense here. Incorrect. So this is incorrect, as it says that all elements are present in X. Option B is incorrect. So let's just say option C now. So option C says it takes and over again over I1, I2, I3, I4, and it says xi1 and xi2 and xi3 implies not xi4. So this is essentially the same statement as this. As you can see, like this implication with the okay, never mind. So what this statement is saying is that I1 and if there are I1, I2 and if I1, I2 and I3 are present in X, then I4 must not be present. Like if I1, I2, I3 are present, then I4 is absent, not XI4. Uh, right. So basically this statement says that if I1 is present in X and I2 is present in X and I3 is present in X, then I4 can't be present. And this is done for like, let's say all possible I4. So what this means is that whenever we come across a triplet I1, I2, and I3, which is present in X, then there cannot exist another element I4 which will be present in X. And this is done over all I1, I2, I3, I4. So I hope this sort of makes sense that this is also true. Like this statement also makes sense because what it's saying is whenever the set X has three elements, there can't exist a fourth element in this set. Because if there exist three elements I1, I2, I3, then some other I4 can't exist. That's why this is not xi4. And this is what we want to say, right? Because we want to say like we don't want to have more than three elements in X. So when we reach three elements in X, we don't want any more. That's what it's sort of saying that there are three elements in X, then fourth can't be present. So this is correct. As it says. So I'm just simplifying what the expressions are saying in terms of English words, as it says that if three elements are present in X, then fourth can't be present. So this just means that there will be at most three elements, right? So let's just go to option D then. So option D is basically, it's not and, it's an or. So it's an or oval or I1, I2, I3 and says xi1 and xi2 and xi3. So this statement just says that I1 should be present and I2 should be present and I3 should be present. And this should be for at least one triplet I1, I2, I3. So this statement is sort of incorrect. It just says that, so this statement basically says that there should exist a triplet which is present in X. But it does not say that at most three elements are present in X. If you get what I'm saying. So xi1 and xi2 and xi3 only means that I1 and I2 and I3 should be present in X. And this should be true for at least one I1, I2, I3. But it does not prevent a fourth element also from being in X, right? As you can see, like for, let's say, all x1, x2, x3 up to xn, all of those values were true. Like if all the value, like x1 to x10, all the values are true, like all 10 elements are present, even then this expression will be true. Because this xi1 and xi2 and xi3 will have evaluate to true. So true or anything will be true itself. So that way it does not mean that there are more three elements in X. There can be any. So this is actually incorrect. So in fact, what we can see is what this statement is establishing is there exists three elements in X. Like it says there exists I1, I2, I3, which are present in X. So it establishes that there are at least three elements in X, not at most. If you get what I'm saying, incorrect as it says. So because if there were two elements present in X, then this proposition won't be true, won't hold true for any I1, I2, I3. So all of this expression will become false. So that's why this expression is essentially saying that X contains at least three elements and not at most. That's why option D is incorrect. So correct answer is like option A and option C. So A, B, C, D are these four options. So yeah. So yeah. So I had some more questions prepared, like 6, 7, 8, 9, 10 questions, but maybe I'll skip the 6th, 7th, 8th, and 9th questions. So I'll be posting this uh, uh maybe I'll just so I'll also be posting these problem statements online so you can access these. So if you guys want to try it out, you can try it themselves, try it yourself, or maybe I'll just delete these questions because I think these types of questions you guys must have also practiced in tutorials. I don't think it's that much necessary to have. So yeah. So we'll just be discussing this sixth question. This is the question which I personally like a lot. This knights and knaves problem. Okay. So this is a very interesting problem. So this will be the last problem for today. So what it says is that an island is inhabited only by knights and knaves. So knights are people who always tell the truth and knaves are people who always lie. So this information is given to us. And now we meet two inhabitants, A and B. A says that B is a knave. B says neither A nor I are knaves. So now we have to, from these two people, whatever these two people are saying, we have to establish who is a knight and who is a knave. So we have to establish this ourselves. So the problem statement I hope is clear to everyone. So there are two types of people, one who always tell the truth, one who always lie. And then we get across two people. We don't know if both are knight or both are knave or anything. But we know that what they say. One says that B is a knave, other says neither A or I are knaves. And now we want to tell who is a knight or who is a knave. So actually this can be converted into a propositional problem. So let's say we take a proposition P, which says that A is a knight. And similarly, we take a proposition Q, which says that B is a knight. So, uh, does this make sense to you? So basically, what we are saying is why we can formulate it as a propositional problem. So if P and Q, if P and Q are true, then A and B both are knights. Let's say P is false, then it means that A is not a knight. And so if A is not a knight, it can only be a knave, as inhabitants only consist of knights and knaves. So that's why we have these two propositions. If we come across like P and Q both are false or P or Q true or something like that, we can tell like if P is true, then we can say that A is a knight. If P is false, then we can say that A is a knave. Same goes for Q and B relation. That's why we have formed these two propositional variables. And now let's just uh, try to take different cases for these P and Qs and see whether these expressions will hold true. So, so what are the possible cases? Either P is true and Q is true. Let's consider all possible cases for PQ, right? So the case one will be maybe yeah. So case one will be when P is true. So this is an ordered pair. So case one will be when P and Q both are true. And I'll try to see this case. So if P and Q both were true. So I don't know actually if P and Q are true or P is false or Q is true. I don't know for now. So I'll try to take every possible case and see whether this case can actually hold. Like if P and Q are true, like let's say I take that A is a knight and B is a knight, then are these two statements consistent with this assumption? So I just want to check whether these statements are consistent with these assumptions. And if these statements are consistent, then this is a possible solution. So I believe the approach should make sense to you guys. That's what I'm trying to say that I'll just see all possible cases. I'll just list down all the cases for now so that you guys can see uh, what the overview of the solution is. So So I'll take all the four cases for P and Q and I'll see whether whether this case is consistent with what A and B are saying, whether case 2 is consistent, whether case 3 is consistent, and case 4 is consistent or not. Okay. So now also let's just see what A says. So A says like the statement which A makes is that B is a name. So what A says is that so if we meet two inhabitants A and B, so A is saying that B is a name. So A essentially says that not B, right? Because A says that B is a name. Okay, it be not Q. So if B is a name, then B is not a knight. So A is essentially saying not Q. And uh, B is saying neither A nor I are names. So B is saying that uh, A and I both are not names. So both are B is essentially saying that both are knights. So B is saying something like this that A is a knight as well as B is a knight because neither A nor I are knaves. So both can only be knights. So these are the two statements which A and B are making. So if A was a knight, then this statement must be true. Not Q must be true. And if A was a knave, then it was lying. And so not Q should be false and so Q should be true, in fact. So this is the approach which we'll be following. So if P and Q both are true, what this means is that A and B both are telling the truth. So if A and B both are telling the truth, this means that not Q is true. So if A and B both are true, A and B both are true. And what this implies is that what this means is that not Q is true, not Q is true, which means uh, Q is false. Yeah. Running out of notation. Maybe I'll just. So basically, if A and B both are true, this means that A is true and B is true. So not Q is true. And this will mean that Q is false. So Q is false. But if Q is false, then P and Q, then this will imply that P and Q is also false. P and Q will be false because Q is false. So A, P and false will always return false, right? So this should also be false, which implies that B is false because B says P and Q, but P and Q is false. But initially we had assumed that A and B both are true, right? Because this was the case, GT was the case. So we had assumed that A and B both are true, but what we come at is B is false. So what we obtain is actually a contradiction, hence a contradiction. So not possible. So this case is not possible. So A and B both are not knights. At least we can say this. So now let's come to the case 2, where A is true and B is false. So A is true, B is false. Right. So what this means is that this statement not Q is true and P and Q is false. So if not Q is true, again we can say that not Q is true. This implies that Q is false. I hope you get the gist of the argument, how my arguments are going. I'm just taking these cases and I'm just resolving whatever comes my way. So not Q was true, so Q was false. So this implies that P and Q, which is what B was saying. So P and Q will be false because Q is false. So P and false will always be false. So this will be false. So this implies that B is false. So because what B was saying was false. So what we arrive at is actually uh, in this case, what we arrive at is whatever B is saying is actually false. And this was what we had assumed in the first place, that B is false. So this is sort of a consistent solution. Hence a consistent solution. So this is a consistent solution. So this is one possible solution. Like note that there can be multiple possible cases true. Like it needn't necessarily be that A and B both are knights. It cannot like one case like these statements might hold true if both are knights or let's say both are knaves. So we need to check for all cases in how many of those cases do these statements make sense. So at least we know that both cannot be knights. One possible solution we have is A is a knight and B is a knave. Now let's just try the other two cases also. So A is false, B is true. And what this means is that not Q is false. And this will mean because A is saying not Q, it will be false. So this will mean that Q will actually be true. And what this means is that P and Q will actually be equivalent to P only, because P and Q resolves to P and true here. Q will be replaced by true. So P and true will be just P only. So whatever B is saying is actually like uh, is actually equivalent to P. And we had said that B was true. So P should, so basically what we had assumed was P was actually false, right? We had assumed that P is false because A is not a knight. We had assumed that A is not a knight. So A is a knave. So this means that P and Q, this will be false because uh, like maybe I'm causing a bit of confusion, but I'm just taking these four cases between P and Q only. So P is true, Q is true, P is true, Q is false, P is false, Q is true, P is false, and Q is false. So P is false and Q is true. In that statement, what this means is that the statement A will be false and statement B will be true. So if statement A is false, this means that not Q will be false, and so Q will be true. And now the statement B is P and Q. And so P and Q will be nothing but we just take the case of, we just put in the value false for P and true for Q, and we'll get a false here. So uh, does this make sense? So yeah. So what we have obtained here is that B is actually false. So this means, so what we have come to this conclusion that P and Q, so P was false and Q was true. So P and Q comes out to false. And if it comes down to false, this means that the statement B is false, which is a contradiction because we had assumed that B is true, which is a contradiction. So this case is not possible. So similarly, in this case, when P is false and Q is false, this will mean that statement A is false and statement B is false. So in this case, what will happen is again, not Q will be false because what A says is a lie. And this will mean that Q will be true, right? Uh, but we had, so this comes to the conclusion that Q is true, but we had assumed in this case that Q is actually false because this was the case of false false. But we have arrived here at Q is true. So this case is also a contradiction. So actually all these three cases, case one, case three, and case four, we are able to arrive at some contradictions. So the only consistent solution is the case two. When so, and case two was A is a knight and B is a knave. So this is the only consistent solution. So just giving an overview of the solution again. So we just took a Boolean variable for A is a knight and P and a variable Q for if Q is a knight. So A is basically saying not Q and B is saying P and Q. Now, these statements might be true or not true depending on whether A and B are knights or knaves. So we consider all the possible four cases for P and Q. So case one was when both are true, that is both are knights. So then we see that these statements cannot hold together. Similarly, when P was true and Q was false, then we found it a consistent solution. When P was false and Q was true, we were again able to arrive at a contradiction. And when both were false, we were again able to arrive at a contradiction. So the only case where we found a consistent solution was case 2. So the only possible uh, way is that A is a knight and B is an A. So I hope this solution makes sense. So since we are running out of time, this will be my last question. And uh, yeah, if anyone has any questions now, like there are like 5 minutes remaining, so you guys can ask if you have any questions in this solution or anything which we discussed before this. So you can ask in chat if you have any questions. So this was the discussion from my side, and I'll try to answer your doubts now if you have any. If you don't have any doubts, then you can leave the session if. Okay, Asif. So recorded sessions, I believe a link will be given to you guys where from where you will be able to see the recorded sessions and also these documents uh, related to the documents in which we are solving all these problems. So I think a link will be put up in an NPTEL post or something. So you guys will be able to know about that. You don't need to worry. Or maybe like after this session, like by tonight, I'll put up the link in this meeting's chat also. The link for this recorded session. I'll put it up in the chat of in this chat only, like in this meeting chat in which we are interacting. So you guys can see this chat also to find the link. Okay. So I'm assuming that none of you have any more questions. So I guess we'll wrap up for today. So this was it for today, guys. Thank you for joining. So hopefully I'll see you guys on next Tuesday also. So yeah, see you then. I'll just stop the recording and you can leave the session. Yeah. Thank you for joining, guys. Bye bye.